Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we go to the Chapter 8 Test and Cumulative Assessment in the Big Ideas Math Integrated Math 2 textbook. Chapter 8 is focused on similarity. We have dilations, we have transformations within those dilations, other kinds we have any sort of type of similarity between two triangles, and similarity within a single triangle when you have things like angle bisectors and a side split thing, a lot of different theorems there. We'll take a look at which problems they have. Only 10 questions in the test portion of this Chapter 8 bit, and then the cumulative assessment, which can cover anything from chapters 1 through 8 in this textbook. In the description section down below, I'm recording now, so I haven't put it up, but I believe I'm going to be putting up for you a PDF of the Chapter 8 test. It's a single page, and then 2 pages, a PDF of the cumulative assessment, and a PDF of graph paper if we need graph paper. So we'll see. I'm not sure. Check out the timestamps down below to find out which problems you want to find, if that is why, in fact, you are here. Hopefully this will go pretty quick. I just did the review portion, which is the one where it teaches a little more. This time I'm probably just going to do the problems. So let's go ahead and take a look at what we have here. I'm ready if you are. And if not, pause the video because I'm starting. Okay, we're going to begin with numbers 1 through 3, where you are going to determine whether the triangles are similar. If they are, write a similarity statement, explain your reasoning. If they're not similar, I suppose we say not similar. And we might have to explain our reasoning still. But so what we're going to look at is these two triangles. I don't know if it's ABC or, I don't know if it's alphabetical. But what you want to do is look at each triangle and find the shortest side for both of them. 18 is the shortest side in triangle ABC. 14 is the shortest side in triangle VUT, whatever order they call it. So I'm going to try and test to see if 18 divided by 14 is the same thing as if I take the mid side of triangle ABC, which is 20, and divide it by 15 here. 20 divided by 15, I'm going to say this answer will be no. But we'll keep moving forward and see if 32 divided by 24, the two longest sides, also share the same proportionality. Is this true? Is this true? Let's see. 18 over 14, you can at most divide by 2 and get 9/7. 20 15ths, you can divide by 5 and get 4. Sorry, there's notifications going on in the bottom of my screen over there. It looks like it's a chat for a group chat for softball stuff. So sorry that I keep poking. I shouldn't look now that I realize that's what it is. Anyway, 4/3. These are not the same. Already this broke. And you divide these by 8. You also get 4/3. That's great that these are the same, but this one's not the same. These are not similar. And my reasoning is because these are not in proportion. Now, if these were all in proportion, if they all shared the same similarity ratio, these triangles would be similar by what's called the side-side-side similarity theorem. If all three sets of sides are similar, are proportional, then your two triangles are similar. Number 2, we have the 110-degree angle measure for both of these. The measure of angle C and the measure of angle J are the same thing, are equal in measure. That's kind of a given. So angle C is congruent to angle J by the definition of congruence. Equal measures, congruent angles. That's good. That does not mean they're similar, though. You would need a case of either angle-angle or side-angle-side. And I don't know anything about any of the other angles here, but it looks like I've labeled sides for which I'm going to try and make that same test that I did before. These are the two sides that make the angle. That's important for side-angle-side. To do this proper comparison, let's divide short by short and long by long. I can test 6 over 8. That by 6 over 8, I'm actually talking about this 6 and this 8, the two shortest sides in both of these. And then let's test out. Let's go to 8, the other on length BC, and divide that by 10 2/3. Now, I'm not a fan of 10 2/3 as a number when it comes to me trying to reduce a fraction. I'm going to turn this into the improper fraction and work that out and see if it works out. I don't know yet. You divide these by 2, and you get 3/4. By the way, this is in question. You get 3/4 here. The question is this 3/4? So this is 8 divided by 10 2/3 is 32/3. Now, I'm going to take 8 over 1 and divide it by 32 over 3, which is the same as 8 over 1 times 3 over 32. 8 divided by 32 is 1/4, and 1 times 3 is 3, and 1 times 4 is 4. You do get 3/4. So they share the same similarity ratio. So the sides are in proportion with each other here. Side-side is not enough of a case for something, but side-angle-side is. So these two triangles are similar by side-angle-side. Triangle blank is similar to triangle blank by side-angle-side similarity theorem. Now, what two triangles? Let's say I called the first one ABC. If I call it ABC, notice that I'm starting from A, going across to B, and then across the long side C to the known angle measure. I want to do the same thing here. Go from K across to L, across to the longer side to the known angle measure J. KLJ. And that's not alphabetical. Triangle KLJ. So there's my similarity statement, and I'm good to go. Side, angle, side, 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 and angle, angle are three ways to justify your triangles being similar. These did not get the side, side, side treatment. They got the treatment. We tested it. It was not approved. But we tried. Last one was side, angle, side. This one here looks like it's probably going to be an angle, angle test. I know that angle X is congruent to angle Y. That is given. Now, there's a long way to get to angle P being congruent to angle Z by saying these two lines are parallel by the converse of the corresponding angles theorem. And then by the corresponding angles theorem, these two are congruent. I could say that. By the way, I shouldn't call that angle X. Let me do that again. I'm not going to go that long way. I'm going to go a little more fancifully. I'm going to call that angle WXP, by the way. Let's look at angle W. Angle W is a shared angle in both triangles that we're referring to that can be noted as similar. There's this triangle here, and there's this triangle here. It's the same angle in both. It's congruent to itself. That's called the reflexive property of congruence. And that's another set of angles in both triangles that are congruent. So this is given. This is the reflexive property. Let me write those out in case you're just writing and you muted me. Reflexive property. Two sets of angles congruent would actually mean the thirds are congruent. You don't need to note that. There is a theorem involved with this that can say we have enough information. Triangle WXP is similar to triangle, look at the triangle, WYZ. Those parts correspond. W corresponds in both that are congruent. X corresponds in both incongruent, or X and Y. P to Z would also be congruent. This is by the angle-angle similarity theorem. Okay. Numbers 4 through 6. Find the value of the variable. This time, they didn't tell us these triangles are similar, by the way, but I think we have enough information to determine that they are, because reflexive property, parallel lines means congruent corresponding angles, all that stuff. By angle, angle, these two triangles are similar, the same way that you saw before. Now, the way that I look at numbers 5 and 6, it looks like that these come a little bit more out of section 8.6. And if you know this information, then we can build off of it. I don't need to go as much in the similar triangle facet. In fact, I didn't even technically need to bring that up. If you have parallel lines in this situation, you can split these sides and build a proportion out of it. 9 divided by W equals 15 divided by 5. That kind of proportionality. 9 over W equals 15 over 5. Yes, you can do one as the parts correspond in the bigger things of the triangles, but I don't have to do that. So here's a setup. I can cross multiply and divide and all that. I could reduce this fraction, but I think these are pretty decent. 5 times 9 is 45. And then here we have 15W. And divide by 15, and you get W equals 3. They said find the value of the variable. We did, and we're good. Number 5 would also come out of section 8.6 of this triangle proportionality, or proportionality theorem, I should say. When an angle bisector, when you have an angle bisector in a triangle, you've divided this into proportional parts. I can divide this by this and make it equal to this divided by this, for example. Do I want to go that way with it? I don't know how to reduce that. Let's do this version. Let's do this divided by this equals this divided by this. And hopefully you can kind of get that correspondence and directionality that I'm pointing out. It'll work. So I'm going to do 21 over 33. And the only reason I'm doing that is because I can reduce this knowingly. equals 17.5 over Q. 21 and 33 can divide by 3 each. You get 7 over 11. And this equals 17.5 over le Q. I still don't know. I multiply 11 by 17 and a half. Your guess is good. I don't even know 11 by 17. I'll work it out. Give me a second. But 7Q equals, I vowed to go without a calculator. Let's do it this way. Let's do 17.5 times 11. 17.5 times 10 is 175, plus another 17.5 is 192.5. Even by knowing that, I don't know what this divided by 7 is. It's not going to be a clean number. So let's start with 192.5 over 7. Is this really the work? That's one version of it. I probably shouldn't box that, though. There's no way I can ever have a decimal in a fraction. It's just wrong. Let me figure out what it divides to. Let me make sure I did the first calculation correctly. 11 times 17.5. Yep, and then divide that by 7. Oh, it's 27.5. That's actually kind of more normal than I thought. 27.5. I expected some weird something else. Okay, then I trust it. All right, number 6. Another angle bisector, but a different appearance this time. And it's probably worth me copying and pasting this over because I need to do some work on this one. So let's see what we have here. Number 6. 21 is the length of the entire side right here. But based on the proportionality we were doing, we want like this over this equals this over that. But I don't know this length, so do I call it x? No. You want to instead relate it with 21 and p. 21's the whole. P is this part. If I subtract p from 21, then I'll get what this length is. 21 minus p. So the same variable is used in two different kind of contexts there. So let's do it. Let's go this over this equals this over this. At least 12 and 24 can reduce that way. 21 minus p over p equals 12 over 24. The p's can't divide and cancel. That's nothing you can do there. I will reduce this fraction this time. I'm going to cross multiply, and on this side I only have p, and on this side I get to multiply 2 by 21 minus p, which means a distribution. That's 42 minus 2p equals p. Add 2p to both sides. Divide both sides by p. You get p equals 14. Find the value of the variable. I did. I'm not double checking or I haven't double checked these, but 21 minus 14 is 7. And p is 14. So 7 over 12 is the same as 14 over 24, and that's true. Cool. Okay, number 7. Given triangle QRS is similar to triangle MNP. Oh, this drawing is for number 8. List all pairs of congruent angles, then write the ratios of the corresponding side lengths in a statement of proportionality. These kinds of questions have shown up in the textbook stuff. I really did feel like, and I think I mentioned this, I think we had a problem like this in the review. I think I made mention that these kinds of questions, I think should be the beginning portions of learning how to do these, and then you start doing them thereafter. I don't feel like they should show up in a review or test, but you got to know how to do it, so there you go. All right, letter order matters. Q, R, S, 1, 2, 3, M, N, P, 1, 2, 3. Q corresponds with M, R with N, S with P, as such that you could state those angles are congruent. I don't have a drawing. I don't need a drawing. I have the similarity statement that tells me angles Q and M are congruent. Angles R and N are congruent. Angles S and P are congruent. The S and P 500. Now, as far as segments, a triangle has segment QR, RS, and QS, and the other similar triangle has segments MN, NP, and MP. Based on letter order, you can do the same kind of things as before that correspond, but they're not congruent. They have a proportionality by side length, such that if I divided QR by MN, I would get the same thing as dividing RS by NP, look at the letter order, and then divide QS by MP, like that. So these are the two things that they wanted us to write. Write or list all pairs of congruent angles, and write the ratios of the corresponding side lengths in a statement of proportionality. There it is. Okay, number 8, 2 parts. There's one slice of a large pizza and one slice of a small pizza in the box. A, Describe a similarity transformation that maps pizza slice ABC to pizza slice DEF. This needs to be copied and pasted or redrawn. Let's see if you can see this well. I think I can see it well enough. I hope that you can as well. So, a similarity transformation. That means you can do a composition, multiple things potentially, because one's bigger than the other. A dilation will happen. We are going from ABC to DEF, so it will be a reduction. And then, excuse me, the dilation might not be what I do first, though. And then there's possibly, I can't tell if this will be a rotation. Oh, there might be multiple things here, actually. But I can't tell if then it's a rotation or a reflection or that you can do either. I think I'm seeing multiple things here, and I'm actually curious to do the dilation first, so then I can move things around. We are going from ABC to DEF. A is on the origin, so if I keep it at the origin right now as the center, I think it can allow me to do the dilation a little bit better. So the first thing I want to do here is dilate triangle ABC. Sorry, I'm getting notifications again. Dilate triangle ABC with the center at the origin at A by a scale factor of 1/2. And I say 1/2 because when I look at these, I see 0, 0, 4, 2, and 2, 4, but this is like over 1 or over 2 down 1 and over 1 down 2. So you kind of have options in the way that you want to state that, but it looks like we need to make it half the size that it was before. So A prime will stay at the origin. C prime would be at this point 2, 1, and B prime would be at 1, 2. This is the reduction. Based on this, we now have what I believe are now congruent, I don't know why that happened, congruent triangles. They are not oriented the same way, though. We need to put this on this thing. But take a look at this. Do I rotate it? I could, probably. Do I reflect it? Do I flip it over? It looks like I could also do that. So I kind of have options, but remember, I'm still right here. Before I do that, I need to like put it in its place. I want to kind of put it right here. I want it the same distance away from the x-axis and really from the y-axis, so I could really do either from here on this next part. So followed by a translation. By the way, this would not probably be called prime anymore. I'm just go with me on what I'm doing there. I did move it over 1 and up 1. A translation of, and I'm going to write the rule because you sometimes see these rules, x plus 1, y plus 1. That means go 1 right on your x's, 1 up on your y's. Followed by, and concluding with, now check this out. You have one of two options. Either one, either with number 1, reflection across the x-axis. So what this would do, your x-axis being right here, is A prime would go 1 away from here and 1 away on the other side of this mirror would be D. It would map onto there. B prime is 3 away, and over here F is 3 away, and C prime is 2 away, E is 2 away. So that will work. The other version, and you saw me kind of do this, I flipped it over like that, and then and it would just go down there across the x-axis. You could also do this rotation, a 90-degree rotation, but what would actually happen in the rotation is it would swing over this way. Now, this is a 90-degree clockwise rotation, so you have to indicate that direction, especially because counterclockwise is the default. So either one or the other rotation, 90 degrees clockwise about the origin. Either or would do that. This was a longer problem because there were 3 different things that you could do there. The dilation was obviously one to do, and move it over so you could get this kind of in the right spot. And both rotation and reflection do work there. That was just part A. Part B. What is one possible scale factor for a medium slice of pizza? Explain your reasoning. Use a dilation on the large slice of pizza. So we have, this is the large and the small. What is one possible scale factor for a medium slice of pizza? Understand that if you're large, let's put it this way. Think of it like, not really a number line, but think of everything from 0 to 1. This is how I'm coming up with this. Where 1 is the largest pizza of the large. There's no XL. Just think of 1 as the large pizza. And then think of the 0 as no pizza. Now, the small size is right here. It's the 1 to 2 ratio, right? 1/2 as a scale factor to shrink the large to that half the size. Not in area, by the way, but just in lengths. The medium has to be somewhere in between these. A valid one, for example, is halfway between 1 and 1/2, which would be, for example, 3/4. There's also possibly 2/3 or something like that, but 3/4 is a possible one. Halfway between the large and the small. 3/4 is halfway between a large and small. And I don't know if that's right. That's an option. Anything between 1/2 and 1, I guess, could be an option. I don't think you would say 99/100ths, but, 2/3 maybe. Okay, I think that one's good there. Okay, number 9. The original photograph shown is 4 inches by 6 inches. You can see the original of the kiddo there, which is the bigger one. I guess we're probably going to do a wallet-sized one after. What transformations can you use to produce the new photograph? I don't know how deep they want me to get in description, but I could talk about a reflection and a dilation. I'm just going to kind of say that. Reflection across a vertical line and dilation by scale factor. It looks like this scale factor may be 1/2 as well of about, I'm just going to put about 1/2. That's not the similar thing anymore. I'm just saying about. It looks like literally it takes two of these lengthwise to make one of those, if that makes sense. But why is it a reflection? The kid has a thumbs up. Oh, that's not a thumbs up. He's holding something. Is that a camera? I think the kid's holding one of those old school cameras. I thought he was doing, anyway, he's holding that, but you can see on the other side, the way the lighting goes, the way that the hand is, that I thought was a thumbs up right there. So it is a reflection. And it's across a vertical line in that, like that. It's across a line like that to make it actually flip over. Okay, I don't know if I was specific enough, but I tried. You dilate the original photograph, by a scale factor of 1/2. So let me say this. Of a K value that's less than 1, a reduction. So let's say I didn't know that it was that, and now they give us the information. That's fine. You dilate the original photograph by a scale factor of 1/2. What are the dimensions of the new photograph? Oh, I forgot that we had the 4:6 as well. So we have a 4:6. This must be the 6-inch. And this is the 4-inch here. Now, the new photograph here, if you dilate these by a scale factor of 1/2, you multiply these by 1/2, which is dividing by 2. So you'll have 2 inches of height and 3 inches of width of that. So the dimensions are, how did they say it before? 4:6. Now they're 2:3. So the dimensions in part B, 2 inches by 3 inches. Part C, you have a frame that holds photos that are 8.5 inches by 11 inches. Can you dilate the original photograph to fit the frame? Explain your reasoning. Question is, can it fit like perfectly? So the question on part C is really a matter of, are these the same ratio? Are they in proportion with one another? So with part C, we have to check, is 8.5 divided by 11 the same as 4/6, or of course 2/3, right? Now, why did I choose 8.5 with 4? Because they are the smaller numbers of the two. You could try and do fraction reduction and stuff, and I'll show you that as well. But what you could also do is, you could also sometimes like cross multiply. If 6 times 8.5 is easier for you, because I believe that's 51. That's 51 there. And 11 times 4 is 44. Those aren't the same. If they were the same, then that means they're in proportion. Now I could also show you the other way here. If we go by fraction reduction, again, this side is 2/3. This clearly won't be equal. 8.5 over 11. If I double those, I get 17 over 22. I'll write that. And that can't reduce anymore. So the fact that it can't reduce anymore is also telling of the fact that those are not the same. So can you dilate the original photograph to fit the frame? No. not in proportion with one another. So there you go. Okay, that's number 9. Okay, sorry, I'm resuming from a pause thing. Couple things happened. I started problem 10. I started reading problem 10, and then I noticed that I had a light on that I normally don't, and I am also cooking something right now, and I checked on that. So a couple things. So I'm going to go back to this. Let's find it. I just totally lost my thing now. Okay, number 10. In a perspective drawing, lines that are parallel in real life must meet at a vanishing point on the horizon. So, and here's the other thing I was going to do. I was going to pop up this image in a better way because that was blurry. That's why I had this other screen up. So let me get this. Because I shrink my PDF on there for you. So let's get the better quality image. There we go. I didn't want to use that small one. So let's see this in a better way. Like that. Okay. Lines that are parallel must meet at a vanishing point on the horizon. So, if you have a train has, it's parallel going like this, but when you see it in a picture or something, those parallel lines just go away like that, so they're not truly parallel anymore. To make the train cars in the drawing appear equal in length, they're drawn so that the lines connecting the opposite corners of each car are parallel. Find the length of the bottom edge of the drawing of car 2. So here's car 2. We need this length right here. Here's some information we have. We have, let me label some of this. So we have 8.4 is this guy, yet the whole thing is 19. So 1 minus the other there would make that as what? 11, 10.6. So 10.6 centimeters there. And with this vanishing point, we have series of things that create like parallel lines, right? So we can do like, I don't know how I can find that length right here, but they have the parallel lines they mentioned were the ones in red. So let me see if there's a way I can do this. I want to draw something for you guys and make it more visible. Let's kind of do it in that same blue. The colors are going to be really hard here because this vanishing point must be the point of a triangle. So like, let's go all the way out to here and here. We have options as far as proportionality goes, not with all known information, but like, I could do something like, this over this equals this over that because the parallel lines. But they bring up these parallel lines here, and I'm actually intrigued by it, and they only mention car 2. So I'm thinking more like, if we do something like these ones, look at kind of that blue. If we do something like this, they do have parallel lines, so we can work out the proportionality, and we have the numbers for it. 5.4 corresponds with the 10.6, or well, 5.4 and 10.6 are the small parts of this triangle. And then as this goes forward, car 2 can be this unknown, I can call it like an X, but car 2 would be this unknown X portion right there, and then this goes to 8.4. So we have those numbers, and I already used the 19 to get the 10.6. So let me see if that kind of makes sense. If I did like 10.6 over 8.4, these numbers aren't great. So this over this equals this over this, like 5.4 over X. Like that. So it's kind of side splitter theorem-esque or triangle proportionality theorem-esque. Cross multiply, I don't know what 5.4 times that is. 10.6x equals, let me do 5.4 times 8.4, 45.36. Hopefully it's a clean number. 0.36. Divide both sides by 10.6 and you get x is, let's see, divided by 10.6. Well, it's not a clean number. I'm getting like this 4.279 centimeters from that. I don't know. Based on this stuff with the parallel, if these lines are parallel and if this works out like a triangle, that's right. I don't know what they meant when they said to make the train cars appear equal in length, because car 1 doesn't look like car 2. I don't think I have to do anything with car 1 there. I'll go with it. If I go to like the nearest 10th, it'd be about like 4.3. So I'll just say that. Looks good to me. I don't know another way to go about that. I think that seems good. Okay, that is the Chapter 8 test portion. Interesting question at the end, but Chapter 8 test portion. Let's move forward into the cumulative assessment from Chapters 1 through 8 and see what we have here. Number 1, use the graph of quadrilaterals A, B, C, D, and Q, R, S, T Okay, write a composition of transformations that maps quadrilateral ABCD to quadrilateral QRST. So this is one of those things, when I look at these, they look like a reflection. Well, hold on. They say the letters A, B, C, D to QRST. No, that looks like a rotation, not a reflection. So that looks like a rotation because the way A, B, C, D goes, notice from A to B is kind of right, and then Q to R is kind of down like that. That's something of a rotation. A reflection would have gone kind of this direction instead. So, yeah, we're going to rotate this thing 90 degrees clockwise, and let's see what this looks like after a 90-degree clockwise rotation. We can hit the dilation after that or before. It's an either or. Oh, Q is on a decimal value, so yeah, let's just rotate it. So C prime goes to here. D goes from negative 4, 4 to, I guess, 4, 4. So D prime. I can't really fit these other points. Okay, I won't do the rotation first. Let's do the dilation first. Let's look at AD's length as 3. And from Q to T, which corresponds, that length looks like 1.5, 1.5. So the first thing I can mention, and I'll do, is dilate ABCD by scale factor of 1/2. Everything looks like it's going to be half the size. So let's see what it looks like when it is half the size, and then we'll mention the rotation. I think is all that's left. So C prime goes to here, which corresponds with S, so that seems to work. D prime goes to where C is, and that's 2, 2. A is at negative 4, 5, 6, 7. So now we're going to be at negative 2, 3.5 for A prime. And then B is at negative 1, 6. So let's go to negative 1/2, oh, I didn't notice that was there. Negative 1/2, 3. B prime. So now this has that rotation, and this is what the new object looks like, kind of like this. So ignore the blue, look at the green, the spotty green, because I'm clicking on this with my mouse. And you can see that this looks like it's a rotation. This thing needs to fall over now and get that. So the next part is followed by a rotation. So let's say followed by a rotation of 90 degrees. Now this is from this chapter. It's from section 8.2. Clockwise about the origin. Okay. That's kind of best I can do for that one. That was part A. Part B. Are the quadrilaterals similar? Explain your reasoning. Based on what I'm seeing, I mean, they said a composition of transformations that maps it. So I'll say it's not based off appearance. If they said you can do it, then you can. But yes, because similar objects can be made by a composition of transformations. Whoops. By a composition of transformations, including dilation, which was really the big one that breaks it from being congruent. So there's number 1. Okay, number 2. In the diagram, ABCD is a parallelogram. Which congruence theorems could you use to show that triangle AED is congruent to triangle CEB? Select all that apply. Here's AED. Here's CEB, and this is a parallelogram. So a parallelogram has several properties. One of them, let's start with its definition, opposite sides are parallel. When opposite sides are parallel, they said congruent, right? You could do alternate interior angles are congruent. You could use the vertical angles that are congruent. And you could say that diagonals bisect each other. So you could use angle, side, angle. You could also use angle, angle, side in any which way because you don't need to do the vertical angles. Ooh, that all wiped out. You don't need to do the vertical angles. You could do these alternate interior angles as well. So anytime you can do angle, side, angle, you can do angle, angle, side. I'm just going to go ahead and say that. So you have that one with these ones congruent there. Side, side, side would work as well. Oh, I got to find out how to undo one versus the other. So let me just kind of circle. Let me get rid of those. So these work. Side, side, side would also work as well because opposite sides of a parallelogram are congruent. diagonals bisect each other in a parallelogram. So there's a side, side, side case like that. Okay. Oh, that's not side, side, side. Side angle side then therefore should also work. Any two sides like that from the diagonals bisect each other in vertical angles, stuff like that. There are a bunch of different ways you can do that. HL is the only one that won't work here. It's not a rhombus. We don't know anything's perpendicular. Diagonals are perpendicular in a rhombus, but these are the ones that would work here. So I'm just going to answer it right there. I hope that's okay. Oh, I'll write it over here because maybe you're following along. So 2, side angle side. Hopefully I answered that correctly based off what I said there. They didn't ask me to explain. I did kind of give justifications, not HL. Hypotenuse leg, no. Number 3, which expression is not equivalent to 20x squared plus 27x minus 14? It's been a long time since we've done algebra. Cumulative assessment stuff, I guess, but outside of that, not really. Plus 27x minus 14. Without looking at the options, I want to do more of the factoring. Let's just play with the factoring. I don't see a greatest common factor, so I want to try and play with two things that can multiply to this. 20 is 20 and 10, 20 and 1, 10 and 2, and 5 and 4. I'm not as much married to the 20 and 1 thought of things, and 10 and 2 wouldn't work because that's an odd number. It's something I've talked about in the past. So I'm going to try the 5 and 4 and see if this will work out for factorization purposes. I'm really thinking about 7 and 2 for this. So plus and minus. 2 can't go with the 4. Let's try it with the 5 and try the 7 here. See what we got. Negative 35 plus 8 is negative 27. I need a positive 27, so change those to a minus and a plus. That's 35 minus 8, which is there. So here's the factorization. Now, what do they have? Which expression is not equivalent? This is just a rewrite of terms. This is fine. That one's good. So that's not the answer. 5x minus 2 times 4x plus 7 is the factorization, so that's not the answer. The plus and minus swaps those to make negative 27x. That looks like that would be the answer. And I should have looked at these. And 4x plus 7, 5x minus 2 is there. That's also not the answer because that does work. So there's a factorization. There it is. Number 4. A bag contains 6 tiles with a letter on each tile. The letters are A, B, C, D, E, and F. You randomly draw 2 tiles from the bag. Which expression represents the probability that you draw the A tile and the B tile? Okay, so your options, I have to think about those things. It's not going to be this one because this is not a probability. That is just a permutation. Same with this one. This is just a combination and permutation. That's the number of ways that you can arrange something. So the difference between doing something there, give me 1 second. The difference between doing something there and a probability, we might use those things, right? They might be used, but it's not really there. Now, I also don't think it's this one here, P. I think it could be close to this, but the thing is, there's not a specific order. The permutation means that order matters. It's like the A tile first and then the B tile second or something like that, I think. And that's not what this would be here. 2 factorial over 6 factorial would be the number of ways that you can arrange something and then another thing divided. You have 2 choices for the first and then 1 for the second, and then 6. I don't think that works with the bottom. I think that the bottom needs more arrangements for things there. 6 choose 2 over 6 choose 4 makes 0 sense. I don't know what that has to do with anything. So it must be this by process of elimination. Let me think about that. Draw the A tile and the B tile. There's only one way that you can draw the A tile and the B tile. It's by drawing them. You might say, what about drawing B then A versus A then B? That's why this is a combination. But there's only one way to do that, and the 6 choose 2 is all the different ways that you can choose any 2 tiles out of the set. So I think it's going to be that one, the 1 out of 6 choose 2. This is something I'm talking through it more than I'm teaching it because I haven't even made videos for that chapter yet. So I'm going to go with that 1 over 6 choose 2. Order doesn't matter. There are this many ways that you can arrange the 2 letters, that you can pick 2 letters, choose 2 letters out of the 6 that are possible. There's only one way that you can get both A and B. That's having A and B. Okay, whoops. Do I want to skip that forward? I don't have much more room. Let's keep moving forward. 4 more questions. Number 5. Enter a statement or reason in each blank to complete the 2-column proof. Let's just copy and paste that and see if I can fit it properly. Fit it proper. Oh, it's not going to be much bigger, but it is what I can do. So, number 5. Okay, we have these two triangles. There's something regarding similarity and such. We have a proportionality. Let me mark that proportionality for us with not congruence, but like this. KJ is to KL as KH is to KM. Hopefully you can understand that because I do. That's given. These two angles, JKH and LKM, are congruent to each other. Why? The vertical angle theorem. Vertical angles are congruent. I'll write that. Triangle JKH is similar to triangle LKM. This is now by side angle side similarity. We have two sets of proportional sides and the included angle congruent for both of them. Angle KHJ is congruent now to angle KML. Where are those? KJH is here and KML. Oh, KHJ. KHJ is here. Let me do this in green because now these are congruent because the triangles are similar. So I'm going to abbreviate that by saying corresponding angles of similar triangles are congruent. I don't know if that's a true abbreviation, but that is the statement you want to make. Number 5, by definition of congruent angles, there are... Oh, you're probably going to say these measures are equal now. You're probably going to say if those are congruent, the measures are equal because you can see that they're using them later. KHJ equals measure of angle KML, and now we use them mathematically. We see that KHJ adds with JHG to get 180 by the linear pair postulate, and then they subtract KHJ over. That is the subtraction property of equality. I don't need to do anything with the diagram right now or explain it. I maybe need to explain it, but I don't need to mark anything right now. Oh, wait. Let me show what the linear pair is. KHJ... Oh, I didn't even see this. KHJ is here, and then JHG is there. So these two add to 180. Apparently, these two add to 180 right there. That's also the linear pair postulate, KML and LMN, linear pair postulate. And then we're also going to use the subtraction property of equality here by subtracting over, I guess, which one do we want to subtract? They subtracted the one that we used before, so probably the KML. I want to see where they're going with this. Measure of angle LMN equals 180 minus the measure of angle KML. So now we have LMN is 180. Oh, the KML, they're going to substitute. KML is going to be replaced by measure of angle KHJ down here. That's a substitution. Property of equality, I'll just put substitution though. So this lent to that. And then by transitive property of equality, we now see two different two different angles equal to the same thing. JHG and LMN are both equal, and it's going to lead to this next. Measure of angle LMN equals the measure of angle JHG by transitive property of equality. Therefore, the angles are congruent by the definition of congruence. So we just show that this, use 3 arcs, is congruent to this on the outside. I'm sure I could have built that up myself, but thank you for helping me. Okay, number 6. The coordinates of the vertices of triangle DEF are this. The coordinates of the vertices of triangle JKL are this. Angle D is congruent to angle J. Can you show that triangle DEF is similar to triangle JKL by using the angle-angle similarity theorem? If so, do so by listing the congruent corresponding angles and writing a similarity transformation that maps. If not, explain why not. Okay, I'm not a fan of it only because of, and I gotta check on my food, but I'm not a fan of this only because of the things being so big and out of my graphing range. I know that there are ways you can do it without graphs, but I really want to display the graph stuff itself, so I'm going to do my best to just simulate it. So D is at -8.5. Yes, I could go by 2s. Thinking about it. D is at -8.5. E is at -5.8. and F is at negative 1, 4. My hope is, when they're talking angle, my hope is this is a right angle here. And it might be. So let's talk about that right now. Let's get into this. DEF. Measure of angle E might be 90 degrees. And here's why. The slope here, let me do this instead. The slope of segment DE is up 3 over 3, which is 1. And the slope of segment EF is down 1, 2, 3, 4 over 4, which is negative 1. So therefore, the measure of angle E is 90 degrees. This is important because for angle, all right angles are congruent. So if this other one has the same thing, we can use that. Now, JKL would probably mean K would be the 90-degree angle as well. So let's figure out the slopes. Let's not draw it. Actually, we might have to still. 16, negative 10 would be like out here. Maybe not quite that far, or maybe quite that far. Maybe like that. J, 16, negative 10. K would be at 10, negative 16. Kind of like down here. Or more. K, 10, negative 16. And then L at 2, negative 8. Okay. And then these connect like this, and then you're hoping that K is the right angle here by checking out rise and run and stuff. From negative 8 down to negative 16 is down 8. From 2 to 10 is over 8. So, oh, give me 1 sec. I have an important email. Let me check this. Hold on. Okay, figured the email out. Okay. If I go down 8 over 8 here, like that's what that will be. So the slope of segment LK is negative 1. It's negative 8 over 8, which is negative 1. And then this one is going to go from negative 16 to negative 10. That's up 6. And from 10 to 16 is over 6. So the slope of segment JK is up 6 over 6, which is positive 1. Now, by the way, when I said these are 90 degrees, I hope you know why. These are opposite reciprocal slopes, which is the reason why it's important that these were right angles, because I don't know how I could find the measure of the angles outside of that. Measure of angle K is also 90 degrees. That means that angle E is congruent to angle K because all right angles are congruent. Okay, so there's that. Angle D is congruent to angle J. That's given. Sorry about this. Something about my food. I might rush now. So this, therefore, triangle, what they call it, DEF, is similar to triangle is similar to triangle JKL by angle. So we do have enough information there. Now the next question that they asked was writing do so by listing the congruent corresponding angles. Oh, okay, well, it's these ones. D with J, E with K, and F with L. And writing a similarity transformation that maps to them. So this looks like a rotation. We're going to be rotating 180 degrees to go around here, and I hope you're getting that because D has to go with J. It needs to kind of go to that side. F kind of stays on the inside with L and all that. And then there's going to be a dilation. Now, F is at negative 1, 4, and when it rotates over, it'll be at 1, negative 4 for F prime. So 1, negative 4, and all the other things will go correspondingly. And it looks like everything has to double. So, you double all that stuff, and that's going to happen. So my transformations are rotate, triangle DEF, 180 degrees. And it doesn't matter which direction, by the way. 180 degrees clockwise, counterclockwise is the same thing. Then dilate by a scale factor of 2. So I'm going to say with K equals 2. That is how that can work out to enlarge to that amount. All right, 2 more questions. Number 7, classify the quadrilateral using the most specific name. This is going to be a parallelogram. It's going to be because we see that the diagonals bisect each other, but that's as much information as we have. We don't know the diagonals are congruent. We don't know that all sides are congruent, that we have right angles. We don't know that the diagonals are perpendicular to each other. So it's not known to be a rectangle, rhombus, or square. I know it looks like a rectangle to us, but there's not enough information for that. Notice that these are 2 tick marks, and then these are 1 tick mark each here, which means they're congruent to each other in those parts, but not the full diagonals as a certainty. And lastly, number 8, your friend makes a statement, quadrilateral PQRS is similar to quadrilateral WXYZ. Describe the relationships between corresponding angles and between corresponding sides that make the statement true. So I'm just going to go with let's write that out. PQRS is similar to WXYZ. I think that's just the thing where you're listing out the angles that are congruent and then the proportionality of sides and stuff. So first letters, P and W, they have congruent angles. Q and X, second letters have congruent angles. And then letters 3 and 4 is the same kind of thing. Angle S congruent to angle Z. So PQ over WX is equal to QR over XY, which is equal to RS over YZ, which is equal to PS over WZ. That's the proportionality. Letters 1, 2, letters 1, 2, etc., and it keeps moving forward. And I think that's all that they're asking for, is just describe the relationships between these things. To make the statement true, these things would have to be so. All right, guys, and that's it. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Within the Big Ideas Math textbook, this is the last part of Chapter 8. You will still see a review thing that I'm going to do with this Are You Ready packet. I've done it for the last couple chapters because my colleague has made reviews. So I still will make one of those, but it might not be in this playlist, but it still teaches this stuff. So thank you guys so much for watching. Take care, and I'll see you in the next one.